You can read. You think I can read this in 1 minute? Yeah. Do it.
You just do this in like 2 hours.
All right, before we wrap up this composition section from yesterday and we get into our new section today, the section we start today, 1.7, is the last section of the unit. So just as a little FYI, because today's Friday, I don't have it on my board yet, I am anticipating a partner quiz on Friday next week. Okay, so I'm giving you a week's notice. And then, no wait, Thursday next week. Partner quiz on Thursday next week. Friday will be a review day, and then we'll have our unit test the following week on Monday. Okay, so heads up if you want to make note of that, please do. On page 70, we still have 2 examples to go over. Is that right? F and J. Okay, so these are going to be good practice for us from yesterday, how we were composing functions, bringing things together, kind of creating something new, and we're trying to ask ourselves, what does the notation want us to do? Okay, what does it look like we should do? So if you take a look at F, can you kind of decipher what that might mean? Yeah? There you go. Okay, so you can think about this as f of x times g of x. I know the x on the end might be a little confusing. You might think you have to multiply it by another x, but that's not the case. So this is actually the same thing. Okay, f of x times g of x. So if we take the f equation and then multiply it by the g equation, okay, we're going to try to figure out what would we get in the end. Now, at first glance, you might think you have to do some type of FOIL process because we're multiplying 2 things together. But FOIL is usually only used for binomials, meaning how you have 2 terms. So notice how the g of x equation is a binomial because you have 2, but f of x is a trinomial because you have 3. So you can't really think about first, outside, inside, last. We do still have to multiply everything together, though. There's not really a name for it like FOIL, but we are going to literally multiply every single term in. You know what I mean by that? Yeah? Okay, so if we take negative x squared by 1, that'll stay the same. Negative x squared times negative 2x, positive 2x cubed. Okay, so we brought in negative x squared. We're going to move on to the 3x. Okay, we're just literally going to distribute everything in. Right, kind of a shortcut way if you think about it. If you're taking 3 terms times 2 terms, you should have 6 terms left. And if you actually count 1, 2, 3, 4, 5, 6, notice how we have all 6 of them. Okay, so 3 times 2, you should anticipate 6 terms. Now that all the parentheses are gone, we can kind of combine like terms. We only have the 2x cubed. We have a negative 1 and a negative 6. So altogether that'd be negative 7x squareds. 3 and 10 would be 13x's, and then the minus 5. Okay, there's our composition. We brought 2 functions together and created something new. What about J? Take a look at how it's written. Can we think about what it's asking us to do? What do you think, Hadley? Yep, g of x plus p of x. Okay, so the g of x equation is 1 minus 2x, and we want to add the p of x equation, which happens to be a fraction. All right, so this is what it kind of looks like at the first step, how we're adding 2 things together. But just like f, we want to kind of simplify it, see if we can make it, instead of having 1, 2, 3 terms, maybe we can just get it down to 1 or something simpler. So this is where we might have to think a little bit. Notice how we're taking this g of x function plus a fraction. If you're going to add a fraction, how do we go about doing that? Can you think about your fraction properties? Go, Jack.
Multiply both sides by x minus 3.
love it, we got to get a common denominator. So if you think about this g of x as over 1, in order to add fractions, we need to get a common denominator. So if this denominator is x minus 3, we got to get this denominator to also be an x minus 3. So we'll multiply by x minus 3 on the bottom. But if you do that to the bottom, you got to do that to the top as well. It's a fraction, you got to keep it balanced. So let's see where that kind of leads us. Now, if we take x minus 3 times 1 minus 2x, those are two binomials, so we can go through the FOIL process. We'll have firsts, outsides, insides, lasts. And we know the new denominator would be x minus 3. So those are matching, which is great. Now that we have a common denominator, how do we actually add the fractions? You want to keep going, Jack? Yeah. There you go. We're going to add all the tops. So we already simplified this top of the first fraction. Let's continue to show how we need to add x plus 2. So put in plus x plus 2. And then we're going to keep that common denominator, x minus 3. So add the tops, keep the bottom. So notice how we now have one fraction. Instead of having a fraction and some other terms, now it's just one thing. So taking a look at the top, maybe we can combine some like terms. Negative 2x squared plus 8x minus 1. And that's all over x minus 3. I like it. Now, some of you, I think we mentioned this yesterday with a fraction, you might feel tempted to cancel out some x's, but remember you cannot do that because all the terms are separated by addition and subtraction. Okay, if they were multiplying terms, that'd be a different story, but we gotta be careful with the addition and subtraction. We're doing okay? I think that was a good review from yesterday. Okay, trying to bring functions together. All right, we're going to switch gears a bit and change to page 73. We're going to go back kind of full circle, okay, back to domain, if you will, and piecewise functions, okay, how we did that kind of at the beginning of the year. What we're going to be really interested in this particular section are trying to identify discontinuities. Maybe you've heard that term before, maybe you haven't. But we're basically going to try to figure out if we have a graph of a function, where does that graph not have stuff that's smoothly connected, if you want to think about it that way. So whenever you draw a graph, it would be very nice if we were able to just put our pencil down and continue to draw. Okay, if we didn't have to lift up our pencil, that would make our life so much easier. Discontinuities, though, are places on your graph where you would physically have to pick up your pencil and go somewhere else. Okay, if you think about the term discontinuous, it's literally not continuous. Okay, it's not fluid, it's not smooth. So maybe as a little short definition, discontinuities are places, bless you, on a graph where the pencil or your pencil is picked up. Okay, a spot on the graph where you cannot go through that location. Okay, you literally have to pick up your pencil. So these discontinuities really show up a lot in piecewise functions, sometimes in other ones, but most definitely in piecewise functions. Because if you think about piecewise functions, and maybe the example kind of in the middle of your page, notice how you have a quadratic, but you also have an absolute value. So you have two different shapes of graphs on one picture. And in order to have two different graphs on one picture, we must have one graph ending somewhere and another graph beginning somewhere. So we're really interested in where does one graph end and the other one begin. Okay, if one graph ends here and the other graph begins here, notice how you would have to pick up your pencil to draw that. Because there's no way you can go from this spot to this spot if you have this empty space in between it. Okay, so that's a discontinuity. maybe one graph ends here and the other graph begins here, but if there's a space in between where they're meeting up, you'd have to lift up your pencil because there's technically no graph there. So we're going to be looking at all these different combinations of where one graph ends and another one begins. Okay, how can we tell if we can draw it without lifting up our pencil, or if we unfortunately have to lift up our pencil somewhere? So we kind of have three scenarios that can happen where one graph ends and another one begins. The first thing is where the pieces, okay, meaning the graphs or the sides, connect at an open circle, or sorry, closed circle, at an x location of A. So hypothetically, maybe we have one graph ending at A, the other graph beginning at A, and where they would connect, there would be a physical point at that spot, okay, a closed circle. Notice how if you wanted to draw that graph from left to right, you could draw it without lifting up your pencil, because the first graph connects to a closed circle, which means you can count it, and the second graph begins at a closed circle, which means you can count it. So you can draw this without lifting up your pencil. This is what's referred to as being continuous. Okay, you can draw a graph without lifting up your pencil. Basically, the two sides meet at a closed circle. Another possibility, if we're thinking about piecewise functions, is maybe the left side stops at A, the right side begins at A, but instead of connecting at a closed circle, maybe they connect at an open circle. We've seen those a little bit this year. So it's a very similar scenario, it's just whether it's closed or open. Notice how this one would be discontinuous, because if you were to draw your graph from left to right, you don't really have an issue until you get to A. You physically have to pick up your pencil, go over that open circle, and then continue to draw your graph from there. Okay, so you have to lift up your pencil at that point because there's technically no graph there. Okay, it's discontinuous. Another possibility at this x location of A is what if the left side and the right side don't even connect at all? Okay, what if they are at different heights on your graph? So maybe the left side is up there where it ends and the right side starts somewhere else. Okay, that is also a type of discontinuity. Okay, the graph is discontinuous. If you were to draw your graph from left to right, you can draw it pretty well until you get to A, and you have to pick up your pencil, go to a different spot, and then continue to draw. Okay, so what we're really interested in this section is trying to identify when these two happen. Okay, when do we have two sides meeting at an open circle, and when do we have two sides that don't even meet at all? Okay, you kind of have that space in between them. Are we understanding the difference between the three? Okay, before we explore these two possibilities, we're going to take a look at an example of a graph that kind of satisfies this first part. Okay, a graph that's continuous. So that means two sides meeting up at a closed circle. Let's go ahead and try to draw the graph. It's going to be a little throwback because we did this earlier this year. But once we have the graph, we're going to try to answer some particular questions about it. So I went over some strategies that might be beneficial to you, whether you want to use them or not. It's completely up to you. But what I first do is take a look at the equations and kind of anticipate what shape of the graph we should have. And if you look at the first equation, notice how it's a parabola because it's a power of 2, but we have that x-axis flip. So that U shape is going to be upside down. The next graph is an absolute value, and there was no x-axis flip, so we should have that regular V shape on our picture. So at least we know some idea. The next thing I do is take a look at the domain section, okay, where those x's are located, and I section off my graph with little barriers. And then I label where each equation should be. So the parabola should be between the barriers, and the absolute value should be on the right-hand side. So that means we don't really have anything going on the left. Okay, we're setting ourselves up for success. Let's actually go ahead and find some points now. So on this first barrier, we're going to try to find a point. Let's plug in -5 in for x. So plus 3 would be -2. Square it, we get 4. Negative out front changes it to -4. Plus 4 would be 0. So if we plug in -5, we get out 0. We got to ask ourselves, open or close circle? Are we thinking in our heads closed? Just because no one wants to say it? Okay, I'll take it. All right, let's go ahead and try to find another point on the other barrier. So that was at 0. We'll plug in 0. Plus 3 is 3. Square it, we get 9. Negative out front is -9. Plus 4 is -5. So we plug in 0, get out -5. There's no bar, so that would be open. So we have two kind of locations for this parabola, but now we need another point in the middle to kind of guide us, because at least we know it should be upside down. The question is, how high does it go? Like, we need that guiding point. How do you think we can find that vertex so we know exactly where the top is of our U? I mean, you can pick random points in the middle. There's 4 of them, so it might take some time, but how can we find this one exactly? Because that's really the only one we really need to help us make this shape. Any ideas? What do you think? Yeah.
HK is like the vertex.
Okay, those transformations are H and K if you're familiar with those. So this parabola moved left 3 and up 4. So our vertex should be located at that spot. Left 3, up 4, somewhere right there. So if that's the top of the U, we can connect our little dots as such. All right, I like that first graph. Let's move on to the absolute value. So let's plug in 0. We'll figure it out where it is on this barrier. 0 minus 2 is -2. Absolute value changes to +2. Minus 7 gives us -5. So we plug in 0, get out -5. It looks like we're on the same open circle as before. But notice how according to this domain, we could equal 0. So it technically should be a closed circle. The new closed circle is actually filling in the previous open one. So whenever you have an open and a closed on the same spot, okay, it's always going to be closed because the closed fills in the open. So we know this is a spot for the absolute value, and it should show up somewhere to the right. But again, maybe we can figure out that vertex kind of as a guiding point for us. If you look at H and K or the transformations, we moved right 2 and down 7. So there's our vertex. So we can make our V shape from there. Make sure when you draw your V, you're accurate. We know the slope on both sides should be 1. Okay, there was no vertical stretch. So make sure you're kind of as accurate as possible. All right, I think that's a good review because we did that a while ago, but at least we're coming back to these piecewise functions. So now that we have the graph, we're going to try to determine, okay, pick apart, is it continuous? Does it have one of these discontinuities going on? Okay, we're going to analyze it. Notice how, if you look at the domain section, the value of 0 is pretty important because that's where this graph ends and the next one begins. So we're really interested in that particular spot. All the other numbers are fine because it's either going to show up on the parabola or the absolute value. What we're interested in is where 1 ends and 1 begins. So notice how the first graph would end a little bit before 0 because we cannot include it. And the second graph would begin at 0 because we can include it. So just shy of 0 and at 0. So that's our interesting location here. So if one graph ends at 0 and the other one begins at 0, can we tell from the graph if there is a defined point at that spot of 0? Is there a closed circle on our graph? Yeah.
Yeah.
What is it?
X is 0.
Okay, so when x is 0, what is the y value? -5. Good. Okay, so that was this kind of closed circle at the very bottom. So notice how where one begins and the other one ends, we do have a physical closed circle at that spot. So it's starting to kind of look like this continuous idea, okay, because we have that closed circle. But just because we do have a closed circle doesn't necessarily mean it is continuous. For instance, if you look at this kind of gap example, I could easily put a closed circle there and an open circle there, okay, where one function ends and another one begins. So notice how just having a closed circle is not enough information for you to determine which one of these it would be. Okay, I could also put a closed circle on this example. I could put one right there. Okay, so a closed circle is unfortunately not enough. We have to take a look at what the sides are doing. Do they meet or are they separate? So let's check that out. In this next box, we're going to have not notation necessarily, but symbols that we're going to have to be familiar with. I want you to listen as I read this, okay? So our first statement here says, as x approaches, that's what the arrow means, okay, as x approaches 0. Now, do you guys see that little negative sign in the exponent spot? Okay, that little negative means from the left-hand side. So as you trace your graph on the left-hand side of 0, okay, kind of coming in this way, notice how the graph is getting closer and closer to that closed circle, which we said had a value of -5. If we check out the right-hand side, okay, that's what the little plus means. If you trace your graph from the right-hand side, notice how you would also be approaching that height of -5, okay, where that closed circle was. So this is kind of confirming something for us. Notice how we know there's a closed circle at -5, but also the left and the right side have that same value of -5. So if the left and the right are meeting at -5 and there's a closed circle there, we have no choice but to determine that it's continuous. Okay, so we have to check a few things. Is there a point there? Okay, because it could be any of the three. But then we got to take a look at what the sides do. Okay, do they meet up or are they separate? Now this was all well and good because we had the graph to go off of, but sometimes we're not going to have that available, and I'm pretty sure not all of us are going to want to graph them anyway. So what we're going to try to do is just look at the equation to help us figure out how can we get these values. Okay, so pretend for a moment that the graph isn't there. Let's check this one out using the equation. If we wanted to check the left-hand side of 0, which equation do you think we should utilize to help us do that? Can you find the one that would satisfy x values to the left of 0 on a number line? What do you think, Hadley? The first one. Yep, if you take a look at the domain, notice how that domain includes values to the left of 0. So we're going to go ahead and choose this equation to represent the left-hand side. So if this is the left-handed side, let's go ahead and plug in that x value of 0, okay, that we're interested in, because that's where the graph is ending. We want to see where it ends. If we plug in 0, we'll get 3 squared, which is 9. Negative out front is -9. Plus 4 would be -5. Notice how that's the same result we got based off the graph. Okay, and we didn't even have to use that because we just used the equation. So we know the left-hand side is ending at a height of -5. Let's go ahead and check out the right-hand side. So if you look at the equations and the domain pieces, that would be the second equation, numbers bigger than 0. And if we plug in 0, because that's our interesting spot, that's where this one is going to begin, we'll get the same -5 as before. Okay? So a graph is not necessarily needed. If we can analyze the equations to help us figure out where does one end, where does one begin, we can see if they match or not. Okay, but we're going to do a lot more of that next week. For now, I just want us to start practicing, can we identify these discontinuous spots? Okay, now there are 2 types, and we're actually going to figure or talk about them by name. So the first one is what's called a point discontinuity. More often than not, you'll hear me call that a hole. And that is where we have the 2 sides of the graph meeting at an open circle. So we'll write that in the little bubble. 2 sides meet at an open circle. The other type of discontinuity we can have is what's called a jump. Okay, that's where we have kind of the gap between the 2 sides. So this is when the 2 sides do not meet. Okay, so one graph is ending and another graph is beginning, and they're ending and beginning at different spots, okay, different heights. So maybe you want to draw an example of that jump. So I just want to practice identifying these 2 different types of discontinuities on the graphs. Okay, we'll get more into these next week, but for now I just want to practice identifying them. So if you take a look at the first one, can you identify a hole or a jump somewhere in that picture? What do you think, Hadley? Where? At 3. Okay, so the x value of 3. So take a look at 3. Notice how if you were to draw your graph from the left to the right, you can draw it really well on the left until you get to 3, and then you have to pick up your pencil and move to the other graph at a different spot. So the fact that you have to pick up your pencil means it's discontinuous. We can analyze, though, what type it is. Notice how the left and the right-hand sides do not meet up. Okay, they're at different heights. Specifically, the first one has a height of 2, and the second one has a height of 4. Okay, different heights. So there's our jump. Let's move down to h of x at the bottom. Can you take a look at that graph and identify a spot where you'd have to pick up your pencil? And if there is a spot like that, can you classify it? Is it a hole or a jump? Yes? Where? Okay, so we're just going to say that you gave me the exact ordered pair, which is fine, but we're going to use the x value. Okay, so hole at -1. So take a look at that spot. Okay, there's an open circle, and notice how the left and the right side are meeting at that open circle. Okay, so that's our definition of a hole. Left and right meet at an open circle. Let's try g of x. Can you identify a discontinuous point? A discontinuous spot? See one, Olivia? Yeah. There we go. Okay, so if you were to draw your graph, notice how you'd have to pick up your pencil at this spot, and the first equation stops at -2, whereas the second equation starts at -4. Okay, so you have those 2 different heights. Okay, jump at -3. Good. What about the last one? What do you think, Nick? Where? Negative 3, 2. Okay, so the x value is negative 3. Perfect. So take a look at this one. You have a left side and a right side meeting up. Okay, they're going to the same spot, but unfortunately where they would meet is an open circle. Okay, that's our definition of a hole. Now it can get confusing because if these two both were examples of holes, notice how this one was simply an open circle, but this one also happened to have a closed circle somewhere else. Okay? That closed circle, whether you have it or not, is kind of irrelevant because our definition of a hole is two sides meeting at an open circle. And notice how that's what we have in both places, regardless if there's a closed dot or not. Okay? Both of them fit that definition. Same thing kind of going on with the jump. Notice how here we had a jump with two open circles, and for this one of them happened to be closed and the other one was open. Again, if there's a closed circle there, it's irrelevant. It's the definition that matters. Notice how both sides do not meet up. Whether there's a closed circle or not, it doesn't matter. Can we see the difference? Understand the difference? Okay. We're going to stop there for today. We're going to take a look at these 4 graphs a little bit more in depth next week. Okay, but trying to get away from the graphs and move it on to the equations is our ultimate goal. Yeah.
Progressively longer, right?